Hello everyone. In this video, I am explaining the concept of linear transformations. This is the first video under linear transformations. Let us understand linear transformation in an intuitive way. See, transformation means it is any change. And this linear transformation is established between two vector spaces. Okay. Now, here to illustrate this, let me consider a transformation from R square to R square. R square is a vector space over R. Okay. R square means geometrically it is a plane, it is a vector space over R. Okay. Now I am going to apply any transformation on this R square on a plane. Okay. So after applying the transformation, there is a change. Definitely there will be a change. Now, the transformation is called as a linear transformation if it maps lines to lines. Means lines will remain lines, they don't get curved. And the second condition is that origin is fixed. Okay. To be more specific, you can say lines will be mapped to lines or a point. Okay. And the origin is fixed. Here I will consider lines to lines. They don't get curved. Lines don't get curved. They remain lines. The position may change, but lines will remain lines and origin is fixed. Okay. For example, let me consider a transformation here. Okay. Rotating plane by 90-degree clockwise. Okay, let us apply this transformation to a plane. So I am considering this Cartesian standard coordinate system. As per the standard coordinate system, this is how the axes are. Positive x-axis, negative x-axis, positive y-axis, negative y-axis, and here is the origin. Now the transformation is you have to rotate this plane 90-degree by 90-degree clockwise. Okay, so after applying the transformation, what would be the new coordinate system? That is, here comes y-axis, origin y dash, it gets shifted by 90-degree. Here comes x-axis, origin, and x dash. Okay, now see, I will illustrate that using this graph. So initially this is the plane and this is the standard coordinate system. Rotate this plane by 90-degree clockwise. So you will have here y over dash and x o x dash in this direction. Okay. Now what happened to the point? Here earlier how to represent a point in the first quadrant? X comma y. Okay. Now what happened to the point here? Now here this axis is y-axis, y, positive y-axis, y comma, this is negative x-axis, so y comma minus x. Therefore, the transformation is represented algebraically as, in terms of mapping, x comma y goes to y comma minus x. This transformation is nothing but rotating a plane by 90-degree clockwise. You have to check, is it a linear transformation? Definitely there is a change now. This is the change. This is how the coordinates are getting changed after applying the transformation. Is it a linear transformation? Look here. You consider a line passing through the origin. Okay. After applying the transformation, that line may come here, but still it remains a line. It is not getting curved. Therefore, this transformation is a linear transformation. And look at the origin. Origin is not going anywhere. It is at the same position. It is fixed. Okay. Therefore, this kind of transformation is called as a linear transformation. Hope you got the point. Lines will remain. If you consider a zero transformation where all the points will go to zero, then in this case you have to specify lines will be mapped to lines or a point. Then origin is fixed. Then such a transformation is called as a linear transformation. Okay, actually when you are speaking precisely, that is how it goes. Okay, in an intuitive way, lines don't get curved. They will remain line. Position may change, but still it is a line. Okay. And origin is fixed. So this transformation is a linear transformation. So algebraically, that transformation is represented as t of x comma y equal to y comma minus x, and mathematically we write the definition of linear transformation as let t be a mapping from two vector spaces, mapping between two vector spaces v comma w, such that first condition is t of alpha v plus beta into w is equal to alpha into t of v plus beta into t of w. Or else we can split the conditions as t of v plus w is equal to t of v plus t of w, and the second condition is t of alpha into v equal to alpha into t of v for all alpha belongs to f and b comma w belongs to the vector space V. If these two conditions are satisfied, then we say that the given transformation is a linear transform. By combining these two conditions, we can characterize it as t of alpha v plus beta w is equal to alpha into t of v plus beta into t of w. This is the mathematical definition of a linear transform. See, this says you the any equation of a line is ax plus by. Okay, that is nothing but a into t of x plus b into t of y. So lines will go to lines, and the origin is fixed using the second condition. It says that it is compatible with the scalar multiplication and vector addition. So if you want to verify it algebraically, then we go with this definition. That definition has to be applied to this transformation. Then that gives you the result as a linear transformation. Now let us consider one more transformation. T of x comma y goes to x comma x square. T is a transformation from r square to r square. Same. Now here it is represented x comma x square. Means y goes to x square. So is this transformation a linear transformation? Whenever you are asked to check the given transformation a linear or not, always remember whether origin is it fixed or not. Here t of 0 comma 0 is going to 0 comma 0. That first condition is met. Origin is fixed. Next, line should be mapped to line. They shouldn't get curved. So let us take the line y equal to x. What are the points on this line? They are 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, and so on. Just check now. T of 1 comma 1, where it goes to 1 comma 1. Then t of 2 comma 2, this goes to 2 comma 2 square is 4. Okay, t of 3 comma 3 goes to 3 comma 9. So initially you had the line like this, y equal to x. After applying transformation, how that transformation looks like I don't know, but this is how it is changing the line y equal to x. So in 1 comma 1, then 2 comma 4 and 3 comma 9. So that line is getting curved. It is nothing but it is a parabola. Okay, initially it was a line, now it is getting curved after applying the transformation. Therefore, this transformation is not linear transformation. This is a one way of understanding the linear transformation intuitively in a plane. Similarly, you can consider one more transformation, t of x comma y equal to x comma x plus 1. Okay. Is it a linear transformation? So y is mapped to x plus 1. So you can see here lines will be remain lines because this is also equation of a line. But the first condition, origin should be fixed. What happens to the origin? 0 comma 0. If you put 0 comma 1, origin gets displaced. It goes to the point 0 comma 1. Therefore, this kind of transformation is not linear transformation. So to check whether the given transformation is linear or not, first always check is 0 comma 0 getting mapped to 0 comma 0. If that is not happening, then it is not a linear transformation. Then you have to check in the other second case, is t of v plus w equal to t of v plus t of w, or t of alpha into v equal to alpha into t of w. T of v. Are these conditions satisfying? If they are satisfying, then the given transformation is a linear transformation. I hope you understood the concept. Thank you for watching.